Okay, so this one's hard because it's just got a lot of stuff going on. There's a lot of parts that you got to think about and remember and plug in, and it's really difficult. So here's where we start. This is the same as the last problem, where it is all about energy transfer. So we're looking at energy initial versus energy final. That's where we're going to start. Okay, so it's all about that energy transfer. Energy initial is actually pretty easy because all we're looking at is going to be the potential energy of the rod. Okay. The energy final is where it's going to get a lot more difficult. So the energy final, the rod's going to have some kinetic energy because it's falling. And the spring is also going to pick up some potential energy because it's being stretched. So those are the three things that we need to look at here. All right. Again, potential energy of the rod is pretty easy. It's mgh. The kinetic energy of the rod, now this is not just falling straight down, this is rotating. So we need rotational kinetic energy, which if you look in your equations, you should have one that says 1/2 I, which is moment of inertia, times omega squared. Okay, we'll talk about that at moment of inertia in a little bit here. By the way, that omega is what we want, because when we figure that out, then we can use that times the radius of the rod and get our linear velocity. So that's kind of our game plan there. And the potential energy of spring, we've used that several times now. That's going to be 1/2 kx squared. Okay. Okay, so there's a couple pieces that we need to figure out here before we get plugging things in. First is I, that moment of inertia. Okay. For the moment of inertia of a rod rotating around an axis, if you look, I think he gave you like a diagram to look at. Anyways, a rod attached at an end should be the mass times the length squared divided by 3. Okay, so you go ahead and plug those in for I. They give you the mass is 0.839, right? Yes. And the length is going to be 0.2. That's squared. Don't forget to square that. And then that's going to be over 3. So when you plug all that in, your moment of inertia is going to be 0.0112, and that's kilogram meters squared. Okay, so that's the first piece of information that you need. The other one is going to be the x, which is how much the spring is stretched. So let's come back over here to this right now. Basically, you have a hypotenuse right there. You have one leg and 2 legs of the triangle. So maybe I should do that in a different color, make it easier to see. There's your hypotenuse, there's 1 leg, there's 2 legs. And if you look carefully here, it does give you the length of all those things. This is 0.1. It's the same as the length from the base up to that center of gravity of the rod. This whole length is going to be 0.2. You can see there's 0.1 here, there's 0.1 over here, so that's 0.2. All right, so now you just use Pythagorean Theorem. I'll come over here, and basically the x, the hypotenuse, or c if you want to call it, whatever, is going to be 0.1 squared plus 0.2 squared, and take the square root of that. And when you do that, you get an x length equal to 0.223. But that's not the exact x length that you want. The reason being is it was already at a length over here of this 0.1. The x really only represents the stretch. So you actually want to subtract 0.1 off of that, which 0.1, which gives you the x that you're really looking for, which is 0.123. Okay, so see what I mean about a lot of things to think about here? Remember, x is how much it stretches, It was already at 0.1, it's now at 0.223, so the amount it stretched is really only 0.123. So now we have all the information that we need. We can start plugging in all this stuff. So again, the mass, we already knew that was 0.839. Gravity, we know is always 9.8. Height, now this is another thing to think about. Remember, we're always going to refer to the center of gravity of the object. So the total length of the rod is 0.2, but that's not where the center of gravity is. So we actually are going to put 0.1 for that center of gravity. Okay. Now we've got 1/2. We know our moment of inertia over here. We calculated that earlier. That was the 0.0112. And omega squared. Remember, we're trying to solve for omega here. Okay, so now we've got 1/2. They gave you the spring constant, which was 22.1. And the x we found over here was 0.123, and that's got to be squared. Let's sneak that in here. So that's going to be 0.123 squared. Okay, now we can start to actually reduce some of these things down here a little bit. So this is all going to be 0.822. That's going to be 0.0056 omega squared. And this is going to be 0.167. So go ahead and do a little bit of algebra there. That's pretty simple. I'll let you figure that out. And bottom line is you're going to get omega is equal to 10.8 radians per second. But again, that's angular velocity. We don't want angular velocity. They specifically said tangential speed, which is linear speed. So that's pretty simple though. You know that omega times radius will give you your velocity, your linear velocity. So now you take the 10.8. This time you're going to multiply it by the full length of the rod, the whole 0.2, because that's what they wanted to know, the length at the end of the rod. And when you multiply those two together, you get 2.16 meters per second for the velocity at that tip. And that's it.